Hello, thanks for joining us today. We're going to be talking about Unit 5 still, Lesson 3, which is focused on tangent line approximations, using the tangent line of a function to approximate that function's values. For this lesson, I like to set the table with a couple pictures. This is also important because this lesson marks the turning point of the course from differential calculus to integral calculus for us. So this is might be the last of the good times for a while for some of you. Here we go. So in the good old days, we would have a function, let's say f. That'll be our function f of x. And we can pick a point on f right here, doesn't matter where. And we could even make a tangent line to f at that point. So when we do that, we get something like, it's really not going to draw for me, something like that. And if you recall, the tangent line, this would be, we'll just label it TL for now, tangent line. So the tangent line matches that point, and because its slope matches the slope of f, in fact, is the slope of f, its behavior near that point is very similar to f. So similar, in fact, that if we wanted to go a little bit farther out from the red point, let's just say this new point over here, this pink one. So here, let's say this is x, and this is some new thing, a new input, we'll call it like x1. So this y coordinate, this point would actually be x1 plugged in to the function that. But let's say f of x is hard to calculate with. Well, what's not hard to calculate with would be this line. And at x1, our y value, because a line would only ever be like multiplied by the slope and then add the intercept, our line's y value would be right there. And this distance between these two y values is a very small gap because of how our tangent line is going to match the graph of f so well. So that's us drawing a picture for more numerical people. I'm telling a story. For more numerical people, I've loaded up a Desmos demonstration. So here's a nice little parabola, and here's the tangent line to the parabola at this point 2, 2. Here are two y values. We can look at the y value 1.062. That's for the green dot, which is on the actual function. And this is the y value of the parabola, which happens to be, the tangent line, which happens to be the line y equals x. I didn't know that until just now. Oops. So as these 2 points get closer, watch these y values. So they're about 0.4 off right now, closer to 0.3. Getting to here, we're only 0.1 off. As we get closer to 2, x value of 2, these y values are getting very close together. To the point here where I have to zoom in to even see the gap. Because we're only 0.023 off. 0.004 off. And then, like I said, at the point of tangency, they're the same. Because this is where the graphs are tangent. This is where the line, that's how I got my tangent line. But when we zoom in really close, the function is really linear. So if I'm close enough to the point of tangency, this line is a good enough approximation. The y value of the line is a good enough approximation for the y value of the curve. One more time with words. So in many instances, finding a value of a function is difficult or impossible with the use of a calculus techniques, namely derivatives. Namely derivatives to get tangent lines. We can approximate the function value by finding a y value on the tangent line to the function. Since this method involves using a linear function, the tangent line function, at a nearby point, linear nearby, we call it local linearization in some cases. So whenever you see the words local linearization or approximation in this context for this Unit 5 test, you're going to want to use this method. The idea is that we have a function, have f of x, and point, let's say, a comma b. We get f prime of x, find slope of tangent line, which is f prime of a will be the slope. We would have a tangent line using the point slope formula. So I'm just trying to review all this stuff before we get into the main videos in a second. So in this context, all that junk would be y minus e equals m times x minus a. And that y is approximately equal to f of x when x close to a. When my x values get close, this gap was small. When my x values, when the x value is close to 2, this gap is almost negligible. Look how close it is right there. You can't even see it. I have to scroll in so far. See, they're definitely not the same. But for our 3 decimal accuracy rule, it doesn't matter. So we're going to get a tangent line, point slope formula, and we're going to use that to approximate. Okay? It's that easy. So we're going to be wanting to use this usually. y1 plus n times x minus x. Okay? Alright, go look at the next video. Go look at some review videos. You could review you could review 2-5 tan line before this video for maximum potency. Alright, that's it for now. Tune in for the next part. Bye-bye.